we're hoping to get there. You can.
Yeah, he comes with.
No, I've got this.
Okay. So he comes with a strong experience in digital infrastructure and enterprise market. So in his role at Neysa, he spearheads revenue growth, market expansion, and customer success. And as you will see that Neysa's goal is to provide cutting edge AI cloud solutions. So Mr. Kurian has a very long a stint of 24 years in the IT sector. He's a rich background in solution architecture, pre-sales and strategic alliances. Before joining Neysa, he had been at the Dell Technologies, where of course, he served at key leadership capacities, including Director of Solution Architects and Pre-Sales for India and Director of Solutions and Alliances. His earlier career also includes roles at Trend Micro as a product specialist and at Sun Microsystems as an enterprise IT architect. So I guess, I will hand it over to Xavier. They are the ones who are basically trying to build stuff. Whatever we are learning in our classes, maybe something that they are doing in practice, right? So that's why it might be of interest to many of you.
Thanks, Anirban. Okay, so I'd like to keep this interactive, first of all. Feel free to ask and we can get into as much detail as you guys want to, right? My objective of today was to go through a few things, but there's a very foundational difference between how clouds have traditionally worked and how AI compute is going to work going forward, right? I'm going to talk a little bit about that. I'm going to talk about how the architectures are evolving, and I'm going to talk about what are one of the challenges that is quite significant, which is cooling it, right? And most of you are younger, but there was a time when we set up data centers at 6 kilowatts, 5 kilowatts a rack, right? One of the data centers that we are currently putting up in one of the floors that we are currently putting up in Bangalore, we are designing for 122 kilowatts a rack, right? 122 kilowatts is probably the kind of power that my apartment consumes. Right? I don't even think it consumes that much. There are 110 apartments. I cannot think it consuming more than 30-35 kilowatts. One rack, and you're going to put up a whole row. So there's a whole bunch of challenges that come with that. I'll talk a little bit about that, right? So first, let's talk about the two types of cloud systems that exist. Now, traditionally, most clouds have been based off CPUs, right? And CPUs comparatively were much slower. Power density, there's a whole bunch of things that came out of that. But there are a bunch of things that were developed as time progressed to solve those problems, right? And fundamentally, if you understand it, everybody understands virtualization and what that is and all of that, right? What it effectively did is it solved the problem of being able to utilize CPUs, right? In the old world, we had 4-core, 2-core CPUs sitting on a server, and you put an application on it, it worked great. When silicon got more dense and they started making 24 and 32 and now 256-core CPUs, you don't need that. So virtualization was the method to go cut that CPU into pieces so that you can go utilize it. Now, the moment you started cutting it into pieces, there's a whole bunch of problems that came. How are you going to run the vSwitch? How are you going to connect it? How are you going to isolate it? How are you going to run security? How are you going to isolate the memory? There's a whole bunch of problems that came. Those are all the problems that got solved by traditional virtualization, right? That's what they went and worked on solving. They went and every traditional hyperscaler worked on solving the problem of how to separate a single resource into many, right? There's a big difference between what is happening with that and what's happening with AI. when you run an AI job, what you're running it on is not one resource. What you're running it on is you're running one job on many resources, right? So it's bang opposite. You're no longer taking you've reached the stage I'm a big believer that the world is a sine wave, so eventually everything comes back. We're going back to that, where you take a single resource, right? You take many of them and you run one job on top of it. And that's what AI demands today. I'm fairly certain that eventually we'll start virtualizing these resources when silicon becomes more powerful or they find something else to do it, right? But today, what you're doing is taking your traditional high performance cluster, HPC, and making it work like a cloud. And that's the foundational difference between the two, right? Now, that went and did a whole bunch of things. So let's talk about networks, right? If you look at the traditional architecture of a cloud, what did it do? You had a bunch of leaf switches. You went and, so between the node and the leaf, you probably had 25 gig, maybe 50. Between the leaf and the spine, you had 16, 7, 20, 23 spines, leaf switches, and you put 2 spine switches. So essentially, if you look at the average cloud in the market today, and this is traditional cloud, you are between leaf and spine, you are typically doing 1:6 subscription. So for every gigabit of bandwidth downward, you have only 0.4 gigabit of bandwidth upward, right? And it gets even worse when you go from spine to super spine. There you'll do another half, which means that any node communicating with another node anywhere else in the network the theoretical maximum bandwidth is about 1:8, right? Now, if you went and took an application that was running on these 2 nodes simultaneously, you've got a problem. And that's the principal problem that AI was looking at solving on the network, right? Where did I put that? We talked through all of this, but now in AI structures, you'll start seeing subscription ratios actually go quite significant when you go to traditional architecture. And there was another problem that everybody needs to understand, that when you start doing things like this, you've got theoretical maximums that you can go and reach. That theoretical maximum is typically defined by how many network ports you have on the switch, right? Let me explain that. If I'm building out a CPU farm, right, and I go and agree that 1:8 is my subscription ratio, a typical switch has only so many ports down and so many ports up. So you've got to sit and decide on day 0, what is my subscription? What is my subscription? How many ports are going to go downward and how many ports are going to go upward? Impossible to change it after. Because to change it after, you have to go essentially rewire the entire data center, which became insanely expensive, right? So when they started building super spines, at those days 100 gig. Nowadays there are people building out super spines with as far as 800 gig. But the maximum number of servers that you could put under a single set of thing and the single pod ended up becoming about 32 switches, which means that if you do high availability, you have 16 switches, which means you can do about 330, 340 servers in one group, right? If you go to, how many of you use PhonePe? PhonePe, you are not sitting on the same pod. The probability is really low. There are 36 pods at this point of time. And every user is assigned to a specific pod, right? So the architecture of traditional thing was to go set up a pod, scale that pod to provide the entire function that the company was expected to do, and then just go replicate that again and again. So traditional network architecture was only about scaling by copying, right? And very often you would copy exact, which means that if a problem happened in one place, it's going to happen in the other place. If you went and ran an update on pod 1 and it broke, you know that you shouldn't do pod 2. You never changed anything anywhere in between, because if you went and made changes, you need new skill, right? So the whole theory of building out scale became a system of building out a stack. Your spines and thing, this much would make one pod, and that pod was fixed. You might go make changes outside that, but the ability to go change a pod became very limited, which also had problems with hey, Intel came out with a new server, AMD came out with a new server. It took time to go make a change, because every change I make becomes a crazy amount of complexity when something breaks. And if any of you have worked in networks, I assure you things are going to break. You should expect them to break, right? So copy exact became a rather ubiquitous word across the cloud industry, which means within the pod, you never made changes, right? And once you set up the super spine, you didn't have the ability to make changes, because you were limited by the total number of ports that it had. Does that make sense? Now, when you were going and building this out, what happened here was essentially then to go build a whole bunch of sites. You went and built a pod, a set of pods connected to a super spine. You connected this through to another super spine and another site, and that had a set of pods, and that had another set of servers below it. So when you wanted to scale, your scaling became pod as the unit, data center as the site as the expansion, and you simply built out other data centers. So I'll give you the example of, and this applies to AWS, it applies to GCP, it applies to Azure, it applies to people like PhonePe that have set up their own, it applies to guys like Netflix that have set up their own, it applies to every, if you are using a cloud service, you're probably hitting an architecture like this, almost guaranteed, because that's the system. You went and I'll give you the numbers. PhonePe runs, if you guys are running PhonePe, PhonePe runs in India on 36,000 servers. On average, 360 servers per pod, 340 servers per pod. Pod sizes came down for the newer pods, right? And 3 sites. So the system was fairly straightforward. You just went and expanded. If you went inside the server, right? Apologies for the drawing, I just drew it out because I think, but every server node that was there, what they went and did is they went and put VMs inside. So you've got 64 CPUs. Each CPU was connected, each socket was connected to a VM, and inside that VM they ran containers. The entire system relies on three nodes in a round robin pair, right? So when you spin up a VM in AWS, right, while it is spinning up the VM on one machine, it is also creating a host instance in the second machine. It's not on. If this node goes down, you can actually spin it up again. It's actually coming up on another node. You don't know it, but it is coming up on another node, right? In the more captive environments, what they started doing is they started doing 3, right? Which means that the entire function of me transferring money to Shoini has become a function that stays within that group of 3. Does that make sense? So if I have to transfer money to somebody, it's inside this instance, there is an app server, there's a database instance, there's a record DB, there's all of that sitting inside here that can make the transfer. If there's a load balancer sitting up there that can load balance each of these nodes. So when user A comes, it points here, user B, user C, D, E, F, and so on and so forth. Machine goes down, doesn't really matter. Right? If a group goes down, doesn't really matter because the data is anyway external. It can, as long as you are inside the pod, the data is on all the machines. If a pod goes down, you have a problem. But yeah, the data is existing, it will take about 8 seconds, it will come up in another site. Right? You started going and building architectures that simply simply relied on load balancing at scale. When you access a cloud service, what you are accessing is actually a load balancer. You are not accessing the thing. You are hitting the load balancer, and the load balancer is then deciding where to send you. If that instance is alive, great. If that instance is not alive, I will spin you up somewhere else. If that site is not alive, I will spin you up at another site. The entire system became a system of how do I go scale this to citizen scale, right? I need to do 50 million transactions per second. Therefore, I need enough resources to be able to do that. I need enough of these small little instances to be sitting there that can do 50 million transactions per second, right? Now, the complexity of this starts becoming fairly straightforward and it looks easy because it's an established system on how to scale, right? The methodologies are fairly straightforward. You're never going to go outside of that methodology. Every major cloud service provider on this, and this is 15 years in the making. 15 years ago, people started doing it. The first people to do it were eBay. eBay were the first people to develop the word called pod-based architectures. And that eBay crowd has now built out every major cloud service provider that exists. Right? Now, let me give you a thought process of why AI clouds are different. Right? AI clouds are, when you hit an LLM, can you run an LLM on less than a GPU? You can, but they'll be really small LLMs. Less than one instance. Can you, okay, let me ask this a slightly different way. If you wanted to scale a language model, would you run it on half a GPU here and half a GPU here, or half a CPU here and half a CPU here? You'd never do that. It doesn't make sense to go do that. Right. It simply makes sense to take one full CPU here and leave the CPU empty, because your losses in virtualization are too steep in this environment. Right? If you need one CPU or one GPU to run the job, instead of running half and half, which is what the whole concept was when you look at hyperscale clouds, the whole concept was to distribute it as much as possible so that whatever fails, it doesn't really matter. Right? It doesn't work in GPUs anymore. It doesn't work in AI clouds anymore. You want to take a single instance and make it as fat as possible to run that job for as much scale as you want, which let me quantify that. If you were running, and I'll take an example. Let's take Llama 3.2, or let's take Llama, right? If you so you can boot it up you can get it up and running and get a fair output of about 180 tokens per second on one H100, right? If you needed 1,000 tokens per second, what would you do? Would you take 10 VMs and run 10 instances of Llama? Is that the right way to go do it? Does it make sense? Is it possible? Yes, it is. But it's a lot more effective to take one full node, use inter-GPU bandwidth that, so if you look at GPU architectures, they have inter-GPU bandwidth that's a lot faster than going across the network. So you'd go take that full instance, run a set of containers on top of it, and run one all those. It's one operating system and multiple containers of Llama. Your scaling becomes a lot easier. Now that's 1,000 tokens per second. What if you needed 1,000,000? A machine is not going to be able to do that, right? Oh yeah, eventually you're going to go the old way, which is the way of distributing it about sites. But if you needed 1,000,000 tokens per second, if your goal was to hit 1,000,000 tokens per second, nothing else, what's the best way to go do it? The best way to go do it is to build a high performance compute cluster that can deliver that can deliver 1,000,000 tokens per second, and it's not going to be linear. So as you increase the number of nodes, your losses in inter-node communication are going to go upward, and you're going to lose performance. So it's not, if one node can give 100 tokens, it's not 100 nodes is not 100,000. Right? It's not linear. You're going to have losses as thing. But you can build clusters as much as you want. Now, I'll give you the other side of that problem. Now, let's say you had 1,000,000, you wanted to create 1,000,000 tokens, but you wanted this to happen across, you've got users all over the world. Right? Does it make sense to build one data center in Bangalore that everybody accesses? No. So you want to build a data center here, you want to build one in Japan, you want to build one in somewhere in the Americas, you want to build one somewhere in Europe, and you want to globally load balance it. Right? How are you going to route that user? Yeah, yes, but so in the old world of transactions, you as a user were stuck to a pod, right? Like I was saying, you as a user for PhonePe is on pod 23. The only time you will see any other pod other than pod 23 is when pod 23 goes down, right? Yep, it does. So, but that's a little different from you accessing a resource. When you switch a base station, you are simply authenticating against another base station. You're still accessing the same resource. Your OSS system and billing system, BSS system is the same within one in the telco service provider. No, it routes to you within the OSS system. There is a pod. The telcos don't really cut that way, but there is a machine in Airtel which has your record, which is how they work, which is how clouds have worked, which is what I spoke about first. Cloud scaled only that way because that's the only way to go scale it. Otherwise, you're going to have copies and copies and copies and copies of data. Your data, Airtel doesn't want to maintain 500 copies of, because if you're saying that it would go to the nearest, billing system, your history needs to be on that billing system. Yeah, I'll be crazy slow, by the way. The moment you want to see, you're thinking of this as 100 transactions per second. Think of it as 50 million transactions per second, right? Think of a telco which has, let's take 1 million users, Geo, right? Now, actually, let's just calculate 1,000,000 users. 1,000,000 users, what's average talk time per user? No, it's not 5 minutes. It's closer to about an hour and 10 minutes, by the way, right? Let's take an hour, right? And they do per second billing because the TRII mandated it. For every second they have to bill, which means that every second they have to log, which means that they have, if they're doing an hour, they have to do 1 into 60 into 60 records for you every day, right? And they have to do it for 1,000,000 users. How many records are they writing? They're writing a record, right? Huh? 3.6 billion. And that's for 1,000,000 users. There are 1.8 billion phones in this country today, right? Take postpaid out of it because postpaid billing is a lot cleaner. Just talk prepaid, 42%, and do the math, right? It is not possible to multi-hop. It is not possible. The bandwidth for that in this country doesn't exist. It is not possible to create the bandwidth for that, right? So, and that's telcos. Think of PhonePe. 50 billion transactions they do in a day. 50 billion, right? Transactions. Now, you're thinking of me transferring money to her as one transaction. It's not. There's the authentication, there's the record, there's the connection that it has to make with NPCI, there's a connection that has to make with her bank, and all of that has to get logged. There's about 8.5 KB worth of data that happens when every time you transfer money. Imagine doing that 50 billion times and doing multi-hops while doing it. Not possible. That's the reason why they said that you as a user are here. I will send you somewhere else only if this fails, right? Now, coming back to AI, when I build out the AI data center, are you as a user tied to one place? Can you be? Really difficult, right? Yes, you need history, you need all of those things, but you as a user are tied to the resource that is available, right? Because if I set up 4 data centers around the world, and this is hopefully I'll be there at some point of time, but if I set up 4 data centers around the world and I said that, hey, you are going to hit my Mumbai data center, and if my Mumbai data center reaches 70% utilization, I'm going to route you to the Bangalore data center instead, right? That's how the AI data centers are going to start working. That's the architecture that's going to start coming up. Now, I'll give you the downside of this. The downside of this is that you as a user, authentication, history, log, everything needs to exist in all my data centers, right? Now, all of this is inferencing. Let's make this more interesting. Let's say I was doing continuous, let's say you went and built a model, SLM, that did continuous fine tuning, right? You're always improving. How are you going to do that? Because now you're resident on 4 different data centers. You're collecting data at 4 different data centers. How are you going to get all the data to one place to fine tune? So it becomes even more complicated. Methods exist, but that's a path for a different thing. There are 2 problems that people have already solved for. By the way, the problem of how I'm going to keep a continuous fine tuning across multiple data centers doesn't exist at this point of time. What most people are doing is they're taking the data from everywhere, bringing it to one place, fine tuning, and updating everywhere. Yeah, it kills a lot of the performance. Yeah, we've actually tried, one of our customers tried it, and it was, huh? Why do you need redundancy for AI? Oh, pod crashes, yes, I understand. The data exists in another place, right? But the data needs to exist only in two places. You're going to collect data in n number of places. By the way, I will have a second site in India before December. I will have a third site by March, April. This is just India. We're talking of 5 countries. That's a small problem. And the problem of distribution is happening not because of the problem of distribution is happening not because I want to, but because that's where power is available. And we'll come to that problem later, right? You need, if you need 20 megawatts of power, best of luck finding that in Bombay today. Not available, right? It's just not available, right? So the first problem that needed to be solved was how do these clusters work, right? And fortunately for us, NVIDIA did a lot of the work in building how it connects, right? They're called fat trees. How many of you have worked on a HPC cluster? Yeah, I guess there's a few of them in this campus, by the way, that I know of at least, right? But most HPC clusters are built off a fat tree. That's the only way to build an AI cluster, right? Because eventually you're going to have to scale beyond a node. You might, if you, as a test bed, you might do 1, 2 GPUs. But eventually when you start scaling, a node is nothing. Somebody like, if PhonePe gives you a chat, you will consume 5 nodes like that. The country will consume 100 nodes before you say hello. And so you've got to go build out these clusters, right? So on the network side, what ended up happening is any node to any node at full bandwidth. You remember I was saying that any node has about 25-50 Gbps? 400 Gbps is really easy to saturate on an AI cluster, right? 800 is coming. There's a Broadcom is just 2 weeks ago released a chipset called Ultra. What? It's the something Ultra thing, and switches are coming. That's going to make 800 possible, which is I'm super excited about it. At least you hopefully will not hit. You'll hopefully will stop saturating the network. What you should also realize is that this is now a game of who can catch up first. The moment Broadcom comes out with 800, models are going to start being allowed to go use it. It's just a question of time before 800 gets saturated. Somebody will come up with 1600. It's a question of time before 1600 gets saturated, right? Are you going to not saturate? Absolutely not, because if all of you have seen an NVIDIA box, that NVL72 box that they've released, that has some crazy number of inter GPU links, and there are folks that are saturating that in training, right? So Tomahawk Ultra, right? So the system of how, but the method of how this is getting built out has now stabilized. The method is very clearly a fat tree. There is a disadvantage with a fat tree. Your disadvantage is 4096 nodes. 4096 GPUs is what you can build onto a single cluster. After that, you're building federated learning. You're building 4096, 4096, 4096, 4096, and then doing federated learning. It's better than building the other architectures. There are other architectures like like Dragonfly and all of that, but federated learning is better than doing thing. And this is, I'm not the expert on that. We've not reached that scale yet, but this is talking to guys like in the Americas that are training things like OpenAI and things which have reached that stage of a problem, right? So the system there is then starts becoming you essentially you have a GPU and you have a NIC on that GPU, right? You have a NIC on the Yeah, so this is for, this is the one GPU that I was talking about, right? You have a VM and you have just that one thing. The moment you start going and scaling this becomes full nodes, full clusters, and it goes all the way to 4086. Now, there's a couple of things that you should remember on this, and these are the places where a lot of change is going to happen, right? Schedulers are becoming a lot better, right? We've done some, and I'm a big fan of open weight, open standard, open source is rare, but open source, open weight models, right? There are a whole bunch of them developing it. The Chinese are leading that charge. GPT OSS went and open sourced their GPT quite recently. The Americans tend to be open closed source, but open weight, right? So you don't know how they trained it, but you can play around with the weights, right? Now, the moment you start fine-tuning all of this, you're starting to use a cluster manager, a scheduler, to go schedule jobs across multiple nodes, multiple GPUs, or eventually, hopefully, multiple sites, right? Now, how that scheduler works has evolved a little bit. We've done some of that work and rolled it back into Slurm, but I don't know how to say this without being but the gold standard on that is a closed source scheduler that NVIDIA developed themselves. I'm a big, this is being a little Indian over here. The moment you don't know how it's working, I have problems, right? Open source is good. IP in India is even better, right? The other piece that's a problem that a lot of people, and the schedulers are going to change. There's a lot of people doing very innovative work on going and solving the problem of how you are going to schedule jobs. But there's a team out of Chennai that is trying to solve the multi-site training problem. Professor Ganesh in Bombay has solved a small portion of it, which is how he got this working as a distributed training. So there's a lot of innovative work happening around that, right? So that was about the architectures. Any questions before I move on to another thing that I'm very passionate about? And now's a good time to ask questions because we can get into some amount of detail. No questions? Okay. So there's one thing that I want to flag off here. I don't think cloud and AI clouds are going to, one is going to supersede the other, right? Their applications are always going to exist, and applications are going to be resident on the virtualized traditional clouds that exist. This is the same way that if anybody of you have seen a Sun Spark system, 72 CPUs, one box, one operating system instance. Beautiful machine, right? It just ran. I know one that is run. I know a 72 CPU system that has not been restarted since 2014. Right? Now those big systems, applications ran on that, databases ran on it, and there is still a place for that in today's world. The cloud architectures that the AWSs and the GCPs and those guys use, there is a place for that. If any of you go and build an application and you want to go scale that application infinitely, it's a great place to go run it, right? The moment you start going and running a model, that architecture stops working, right? Because those architectures weren't built for it. Those architectures were built for cutting into pieces, not blending everything together, which is one of the reasons why I think GPUs are so expensive on those cloud platforms, because they are using a whole bunch of network and trying to group it together. It's too expensive for them to do it, right? so the space for application hosting will continue to exist. The space for hosting AI applications is changing, and it is changing faster across the board. Does anybody know where OpenAI trains? Who owns OpenAI? Majority stake? Microsoft. Microsoft's biggest money comes from Azure. Where does OpenAI train? Wrong. Huh? Has anyone heard of a company called CoreWeave? That's where they train. American company. They run the new architecture, right? Sounds very odd, right? That would happen, but that's already happened in the Americas, right? There's a site outside of Phoenix. If any of you fly into Phoenix now, if one of the airstrips, when you fly in, you'll see a whole area that is becoming a building. It's going to be, and I'm not kidding. Okay, you will fly a good 4 seconds over it, right? It's a data center. It is a data center, not 20 different companies, right? So this system of going and building out these large scale architectures is starting to become fairly ubiquitous. There are 3 players in India. We are one of them. I won't name the other 2. And at this point of time, we've already built out one site. We're building out the Bangalore site. We've already contracted the Delhi site, and the intent is to do Japan and Europe after this. This is just a little bit about us, right?
So one question. So in this era, for example, I mean, we know that even Elon is trying to.
Yeah, that's the data center I flew over.
So
Yeah.
the Arizona one. So he is getting a lot of cars, right? For example, he has direct connection with NVIDIA and so on. But my point is, at some point of time, these cars are becoming obsolete, right?
Yes.
In some sense. But
Yes.
it's becoming obsolete for somebody, but it's not becoming obsolete for somebody.
1 year is the current estimate.
Right. So is it possible to handle, for example, if I bring in more cards and if I want to increase my capacity as a data center and so on and so forth. So is it possible, how difficult it is to handle such heterogeneity?
So I will give you what we are doing, right? And I don't have an answer for that scale as yet, right? Hopefully we'll figure that out when time comes. But on day 0, let's say I go get 1,000 H100s, right? You run training. The trainers are the ones that want the least, because the losses that you get as you scale is actually quite significant. At the end of the year, you come and tell me, hey Xavier, I don't want these H100s, give me B200s. Done, I switch you over. These H100s are great inferencing GPUs, right? For training, it makes a big difference. For inferencing, I can run what token as a service, and as long as I load balance users, I can go cut it into pieces and go make some money out of it, right? So the use of the GPU as time progresses is going to change, right? So just so that you know, we went live September of last year, right? Next month we will use inferencing. We will launch inferencing as a service. These are GPUs that are already a year and a half done, right? We're going to take a bunch of H100s and move them to inference as a service. That will run for about 2 years. At the end of 3 years, the GPU is junk.
So
it has.
You will still need critical volume of GPUs of each.
That's the downside. Yeah, that's the downside. You need about $50 million per cycle of purchase. Yeah. I'll give you the other problem. You cool it by sending water into a coolant into the server. Right? and you and I can talk about all the problems that exist with this, I will still tell you it's worth it. Now, let me explain why. Does everybody understand what PUE is? Power usage efficiency. So, 20 kilowatt server, how much do you think it takes to cool the room? You have to run air conditioning, right? How much do you think it takes to cool? No, never more, about 10 kilowatts. If you have a PUE of 1.5, if you have a PUE of 1.5, you are essentially using 10 kilowatts in cooling infrastructure for every 20 kilowatts that you're burning in a data center, right? Now, one of these nodes is 8 GPUs. If I have 1,000 GPUs, and let's say I have 4096 GPUs, I will be there in short order, to 1.15 or 1.2. That's a small city. A small city, right? That's the goal, right? There are all sorts of problems because of it, right? The way you do this is by taking a coolant, which is radiator fluid. What is it called? It is radiator fluid. The green color radiator fluid, but it's called. It's not a refrigerant. Refrigerants are we tried refrigerants, and I'll come to that. We've got another. I've got immersion. For immersion, refrigerants work, right? So I take a coolant, pipe it inside, run it on a set of fins, cool the pieces that are hot, and take the hot liquid back out, right? Now, here's the nice thing, the reason why you do it, and I was talking about PUE. How many of you have been in a data center? How is it cold? Fairly, right? Do you know why? No, because air is a terrible conductor. It's really bad. You guys are physics, right? So, the only way, what temperature does silicon work at? What temperature is your CPU? What's core temperature of your desktop CPU? 60. Why can't air be at 50? Because it won't get it down to below 60. If you're running a coolant, can you? My inlet on these servers is at 55. Outlet is at 67. If I take 67-degree coolant and just run it through a radiator with wind passing through, it will come back down to 55, right? Because of which it's a lot more efficient to cool. You're not running a compressor, you're not running any of those good things, right? Now I'll give you the downsides, right? You get the slope of that wrong, you get the slope of this pipe wrong, and you'll have pipes bursting here and not enough flow over here, right? All of these coolants are typically corrosive. So material science, materials are. I'm a mechanical engineer. I realized how important it is only after I started doing this stuff, right? So a number of things that can go wrong is orders of magnitude higher, and you are doing it to save a city's power, to save the power. It's not small money, okay? Take about 8 rupees a kilowatt hour, do the math. On a 4,000 GPU system, you're saving about 28 crores of rupees a quarter. 28 crores in a quarter, just power bill, right? This looks cheap after that. Taking all this pain looks really cheap after that, right? Now, this is air. There's a couple of which is the DLC, the direct contact liquid that I showed you, right? You see this piece? Those are flat tanks. The racks are lying down. That's the next things that we do, which is to drop the whole server inside a coolant, right? Two-phase immersion, we've got a test bed of it, and that's where we use refrigerants. The problem with that is that all of these refrigerants are toxic, and we weren't able to, and GPUs are notorious for failure. 3%, if you buy 1,000 GPUs, 3% of them will fail within the first 3 months, and you have to open this thing for it. So it became very painful to go do. Immersion can get PUEs down to 1.07, but then it's a whole new set of problems. So absolute whole new set of problems, right?
So here you are assuming 40 to 94K B200s.
This is a sample, but we are actually the thought process is to put 7 B200s inside one tank. No one's done it yet, by the way. This is all tests, and if you see, they're all one tank that's there. The data center I showed you is a CPU data center.
Because when you are mentioning these PUEs, you are primarily having that goal in mind.
Yeah.
It's because we have one space that's running on 1.1 PUE.
Which
The data center.
air cooled DLC. You're taking mechanical, or you're taking end to end? Where are you measuring? You're measuring at the
We are measuring end to end.
at the transformer.
Yes, 1.1.
That's really good. That's really good, by the way. 1.1 is really good for blended PUE. I've not got DLC at that low. I've got it at 1. Cold ones can get as low as 1.17, 1.18. Hot ones are at 1.22, 1.24. Right? And I've got 3,000 in one place, 6,500 servers in another place. Right? So, but DLC is expected to be a lot better. If you are at 1.1 on DLC, immersion will at least be another 0.5, half of it, at least, right? The reason for that is that this can again run at very high temperatures. You don't have anything that you're not cooling. Your memory, your chipset, your NIC card, everything is cooled with liquid.
What about scalability? We haven't worked with immersion, so are we assuming that whatever goes into one particular immersion tank, they're all going to be self-contained?
Yeah.
Is there any possibility of networking?
You typically put the network on a rack at the side of it. So if you go back to that, see, this is the tank. That's the there's space between. Those are two racks.
So you can still do a factory between these tanks.
Huh?
You can still do a factory.
Yeah, of course you can. Of course you can. No factory, no point. Right? The reason we limited to 7 is because that's where the 48 port switch limits. It's a network limitation rather than anything else. So immersion, yeah. Polyalpha olefin. Oh, I would have written that on my other one also. Then what? Propylene glycol. So the downside of this is that it's a little pricey at this point, right?
Question was about electrical
Oh, you can dip your hand in Power 4, take a live wire and touch it, you won't get a shock. Obviously, if you touch the tip, you will because you are penetrating the oil. But if you have a thin film is enough, you won't. Thin film is enough for thing. And the liquid is non-toxic, non-conductive. Polyalpha olefin is probably really good for it. You can eat. You don't have to wash your hands before you eat after maintaining. So.
So just trying to read the OEM. So this is
GRC.
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 Earlier, I think 3M was the.
The liquid is made by 3M. The liquid is made either by 3M or by Reliance Industries. Reliance Industries has just started making in India, because of which we are expecting the price to come down quite significantly. Right? And now I'll give you, yeah. No, 10 years. Right? If you know somebody that has run it for 10 years successfully, please let me know, because I don't. That's what they claim, right? At this point of time, pinch of salt with everything like that. There's a lot of downsides to it as well. All plastics leach, all plastics have emulsifiers in it. The emulsifiers leach into polyalpha olefin, right? How it is going to react over 5 years at this point of time, I don't know. I don't think anybody knows, right? So the question is, can you design the plastics inside to limit the leaching? There are people working on it, but I'm the cloud. I'm not the engine. I'm not the guy designing this. Not anymore. I used to be. Right. Even your cables, for example, your power cables, they need to be different. Your Ethernet cables, they need to be different. Optics need to be outside the liquid, because otherwise, or they need to be sealed. So everything that you put inside immersion ends up becoming a lot more expensive. Sealed optics are about 6 times as expensive as regular optics. Right? But the efficiency gains are significant, and the one thing that you have to remember is that the big difference comes here because you're not running any fans. Oh, by the way, do you know how much power your fan consumes in your notebook? I said 30 watts. How many watts of that is the fan? If it's 0.5, I'll be impressed. It's about 5 watts. About 5 watts of 30 watts on a notebook is a fan. If you take that's 500 watt server that I was talking about, almost 80, 90 watts is a fan. The 14 kilowatts on a GPU node, 3.5, 4 kilowatts is fans, just moving air. Immerse it, no fans. Right? So there are advantages. There are also significant disadvantages. Right? There are also significant disadvantages, and the disadvantages, and many of you are studying. Please start working on some of these problems. When you go solve one of them, please come and say hello to me. I will experiment. Right? The number of problems that exist in, is it going to become the standard way to do data centers 5 years from now? I'm 100% sure. Right? Is there a see, if you want me to build an air-cooled data center, I can do it in my sleep today, right? Because I know exactly what you need, right? You tell me to build a liquid-cooled data center, I don't sleep for a month, right? Because there are 100 things that can go wrong, right? That's the 2 things that I wanted to talk about, but we started on this slide. I want to end on it as well. One is not going to replace the other. I want to point that out, and I want to be very clear about it, right? Both systems are going to continue to exist. I'm not given the history of traditional data centers, it's really difficult to find innovations that improve on how clouds run. Very difficult, right? But you should also understand that if you can get 0.02% better performance in terms of transactions per second, and you come up with that idea and go give it to PhonePe, you are done. They will lap it up. Like 0.02 is a lot for them. If you're doing 50 billion transactions and you get 0.02% extra transactions per day, it means that they're going to save $8-9 million that year, right? The world of AI clouds is changing incredibly fast, right? We've built our system. We've decided this is how we are going to go do it. There's some very smart people in my company. And that are far better than I am to go and design some of these things. But what we're doing is we're gaining on experience that has come from building the data centers and liquid cooled and immersion sites and all of those things, and saying that, okay, this is the right way to go do it. Is there going to be a crazy amount of development that happens in this world? Absolutely. Are new architectures going to come? I think the factory architecture has stabilized. Is it going to get faster? Yes, it is. Is there a lot of work that's happening on file systems, on cooling, on how storage connectivity happens, how to reduce latency while doing distributed training, how the software stack works in terms of schedulers, in terms of all of those things? Yes, there is. And all of those things are going to incrementally add value over time, right? One of the things that we are very happy about is our ability to go, one of the things that I'm actually happy is an understatement. I'm very proud of is the fact that we are able to adapt to some of these changes really fast, right? So that's about what I had to talk about today. I'll leave you with a very small little change that happened quite recently. So there's this customer of ours that runs voice models, right? That voice to text, right? Now, all of you have used a voice to text model. Have any of you used a multimodal voice to text model where it will also give you sentiment? No? Okay. So they're starting to come. Llama is one of them. DeepSeek does it quite effectively, etc., etc. Now, when you start running voice streams through a GPU, where are the problems? The L2 cache fills up. Correct? That's the first thing that's going to happen. So your limit of how much voice to text you can do is not determined by the power of the GPU. It is determined by how controlled you can be on streams of data going in. You're right? With all the efficiency, with a month and a half of work, we went from 4 streams to 5 streams. Right? Then along came Furiosa.ai, what Korean company that built a purpose-built GPU to run voice. What did they do? They took a much lower powered GPU and they slapped a ton of L2 cache onto it. 16 streams. Right? The thing that's going to happen here is effectively that. There are going to be forks that start coming out, right? There's going to be, and Furiosa is one of them. There are 5 other options that will pop up, right? But there's going to be, NVIDIA is the giant in the space today. And when I say giant, I mean giant. 93% of market, right? But so was Intel 10 years ago. Intel is 60% of the market. AMD is a cool 40 on the CPU side of the world, right? AMD is 2% today in the GPU side of the world. NVIDIA is 96. 2% is everybody else, right? The ecosystem, when the ecosystem starts changing, it is the flexibility that gives advantage, right? And that ecosystem is going to change. All of you are at a very interesting point of time of the tech curve on AI. It's a brilliant time to be in this space. I'm enjoying myself. So that's that's about what I have. I'm not going to talk about what we do and all of that. I think I've talked a little bit about it. I'll just leave this there. This is effectively what we've gone and built as far as the software stack goes. Questions? Mm-hmm. I didn't get the question. What are you?
My question is, who are these people apart from these problems, like as you mentioned, a lot of problems like heating?
Okay, I will give you an answer. So if you look at the market, and I'm talking about India today, right? There's the research side, obviously. There's IIT Bombay, IIT Kanpur, you guys, all of you run a bunch of GPUs. That's core research, right? At this point of time, it's about 20% of the market, right? And falling, because the rest of the market is climbing faster. It's actually not falling as a number, it's actually increasing at a number, but it's not increasing as fast as everybody else. The big growth is happening in the startup ecosystem, and I'll give you some examples. Have you guys used Dashtun? Have you guys used Gyani? Have you guys used, give some names, Shoni? InVideo? All of you are, how many of you are on Instagram? Everybody, I'm assuming. None of you have used InVideo? It's awesome to go create videos, right? Good. I dislike Instagram, by the way. So, there are, and all of these are examples of citizens' consumption, of consumer consumption, right? I'll give you another example. Does anyone have an Axis Bank account? Yeah? Have you tried chatting with Axis Bank nowadays? Within the last 2 months? Try. It's actually awesome. It's gone from wait, this, that, it's gone to, and real answers. You can ask it, what was my total NEFT out of my account last month, and it will give that to you. And you can then say, break that down to me by type of transaction, it will give that to you, right? That all of this is consumer consumption, right? I'll give you the example of enterprise consumption. There's this manufacturing company in Pune, right? And they had this problem. They have 8,000 people that come into 3 shifts a day, right? They work with molten metal. On average, they would have about 3 accidents every month. And accidents in a place where you work with molten metal normally results in losing limbs or life, right? If you go back in history and you look at what causes accidents, the primary cause, and I'm talking 75% of all accidents, are because of alcohol consumption. Now, you may think of it as thing. It's not people drinking and coming that morning. It's people that drank too much the previous day and have not got all the alcohol out of their system, right? So they wanted a way to how to detect alcohol consumption. So they have a gate and they have a 200-meter walk to the next gate. They put 4 8K cameras, 2 at the sides, 1 at the back, 2, I think they put 3 in front, right? It takes snips of your eyeball, of your iris and movement pattern. It takes 16 frames, 1 second of everybody that's walking through. detection rate is 97%. It is highly accurate. Do you know what the number of accidents has been in the last 4 months? 1. Do you know what happened? The bigger factor is that workers realized that you will get caught. Right? And that's great for the company. It is actually great for the company. You don't think of it as much, but for that company, it was the best thing that ever happened. Do you understand? Do you have an idea of how many GPUs that's running on? Do you have a sense of that? Make a wild guess. 8,000 people transfer in 45 minutes, 3 shifts a day. How many GPUs do you think it takes to go process their eye movement? 64. H200s. Right? That is one use case. That is one use case. Does it matter? What's the cost of 4 hands a month? Huh?
I have a question that is slightly more off track. Whatever is looking at, like, since you're a startup company, I don't know, maybe now it's not a startup anymore.
No, we still are very much a startup.
Okay.
Yeah.
How did you gather all the resources, like supply chain management? How did you manage them? Can you give any talk, idea? Like, how did you gather all these assets?
That is a conversation for lunch. But let me tell you, give you the short answer to that with a lot of pain. So, but there is no shortcut to it. If you are thinking of starting something, there is no shortcut. There is only one way, and that is.
Again, my question was to, who are these people, who are putting money into startups like you, who are building
So I'll give you a more quantitative answer to that. At this point of time, I am onboarding 3 customers on average a week. Right? And this is not the research. These are startups, enterprises, banks, fintechs, etc., etc. PhonePe is a customer, JustPay is a customer, Paytm is a customer. That's a fintech. Banks, HDFC, ICICI, Axis Bank, Ujjivan Bank. There's a whole list, right? Enterprises, manufacturing companies. I'll give you another example. There's this. This I'll make more money-wise, right? So, do you know what wire harness systems are? All of you have a bike, car. You have a switchboard. You have a fuse box over there. Open the fuse box. There's a whole bunch of wires going to everywhere in the car. Who makes that? Wire harness manufacturer, right? Now, if you're making a car, you're making the same car 100 times. You can standardize the wire harness. But what if you're making it for Dassault Aviation or for Tejas? If you're a wire harness manufacturer that makes one of one, or for Siemens that makes medical equipment, it will be different for Manipal Hospital. It will be different for Aster Hospital, because the things are in different places. Somebody has to make a custom wire harness. So there's this company in Delhi that's the absolute gold standard for it, right? Their method was very simple. Siemens would or Dassault Aviation would send them a drawing, right? Somebody would sit down, they would map each wire, mark the connectors, look at distances, how much to strip. It was a nice 20-day process. They would write a bill of material down, and they would send the Dassault Aviation a quote saying, this is how much I will do this for. Dassault would give them a PO, they would manufacture it, and they would send it back, send it to Dassault. Average failure rate, ISO standards, 0.04, 0.05. Now, this is a YOLO lookup, right? You can do the bill of material quite simply. So they used Llama. They took a photograph of this drawing, right? Or if it came on PDF, you could just import it. The model would look at this entire thing. It would look up a database. It would, by the density of wire, it would decide how much how much it has to strip, and it would do a bill of material, work estimate, and churn it out in about 4 minutes. Right? 2 GPUs. One use case, 2 GPUs. That same customer also does 10 other use cases. But this one by far saves him a pot of money. A pot is an understatement. Right? So the answer to your question is that, and this is what I was talking to Professor when I walked in, the things that we are solving today in this country are very pillared, you're solving a problem. The Chinese have already started going and solving multimodal problems, right? And it's happening in the Americas a little bit as well. Then I'm not saying that there aren't guys in India that are doing it. There are, but it's the rare phenomenon rather than the common one. In China, it's 50-50. In America, if you go to Silicon Valley, it's about 25-75. The rest of America is terrible at it. So the use cases that you can go develop, the ideas that are coming out of the ecosystem today that can go and solve point problems are phenomenal and absolute value for money. The problems that are being solved that are more complicated are rare, but they're starting, right? All of you have a scooter? How many of you have an Ather? Ather scooter, electric Ather? Nobody? Huh? Pretty cool, no? Huh? 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 Pretty cool, no? Even I thought it was damn cool, right? So,
So I have one question. So this, if let's say for us, for example, we want to build, we are small scale consumers, right? So of course we go to you for high end and variable requirements and so on. But let's say when we are building our own resources, right?